Today we are going to start our second module, and the syllabus actually covers the standard test signals, time response specifications, time response of first order and second order systems to unit step input as well as unit ramp input. Then we have the time domain specifications, steady state error and static error coefficients, and finally the dynamic error coefficients. So these are the topics that will be covered in second module. So we will start with the time response. So how do we define a time response of a system? The time response of a system can be defined as the output of the closed loop system as a function of time. So time response is the output of the closed loop system but as a function of time. So generally we all know that the transfer function represented by C of s by R of s is equal to g by 1 plus gh, or in s domain we can represent it as g of s by 1 plus g of s h of s. Actually when we say time response, it's actually c of t, and the Laplace transform of that c of t is this c of s. Okay, so what would be c of s? If we have c of s by R of s is equal to g of s by 1 plus g of s h of s, then c of s is equal to this R of s into g of s by 1 plus g of s h of s. Right. So we know that c of s equal to R of s into g of s by 1 plus g of s h of s. Right. So how do we get the time response now? So if we know c of s, then we can easily find out the time response c of t by taking the inverse Laplace of c of s. So this c of t is the response in time domain, or the time response. That c of t is equal to inverse Laplace of c of s. So that is L inverse, or inverse Laplace of R of s into g of s by 1 plus g of s h of s. So here g of s by 1 plus g of s h of s is represented by this m of s. So that's the time response. And actually this time response has two parts. They are the transient response and the steady state response. So our time response of a system has two parts: the transient response and the steady state response. So the transient response is actually the response of the system when the input changes from one state to another, whereas the steady state response is the response as the time t approaches infinity. Okay. So now we are moving on to the next topic, which is the standard test signals. There are several test signals used in control systems, and actually the knowledge of these test signals is required to predict the response of a system, because in practical cases we don't know so what would be the input, or what would be the nature of the input. It might be random in nature, so such inputs might have the characteristics of some basic signals like step signal or impulse or sinusoidal signal or ramp or parabolic, etc. So such basic signals are known as the standard test signals. So we need those signals to predict the response of a system. Okay. So because we do not know the actual characteristics of the real input signal in practical scenario, so in that case in order to predict the response of a system, or in order to predict the behavior of a system, we use certain signals which has the characteristics of a real practical signal. So such signals are basically step signal and unit step signal. Then second one, ramp and unit ramp. Then we have a parabolic signal and unit parabolic signal. Fourth one is the impulse signal, and finally the sinusoidal signals. So by sinusoidal signal we mean both sine wave as well as cosine. So some kind of sinusoids, that's it. Now how would we represent a step signal? So step signal u of t. So u of t is equal to a, amplitude a, for time t greater than or equal to 0. For t less than 0, u of t is 0. So that is a step signal. And this step signal becomes a unit step signal when its amplitude is unity or 1 for t greater than or equal to 0. And for t less than 0, like the previous case, u of t is 0. So that's a unit step signal. So this is how we draw the signal. Okay. Second one, we have the ramp signal. So ramp signal is a signal whose value increases linearly with time t. Okay. So let the signal be r of t. Then r of t is equal to a into t for time t greater than or equal to 0 and r of t equal to 0 otherwise. So this is how we can draw the waveform. So when t equal to 1, r of t will be a, and when t equal to 2, r of t will be 2a. So the signal increases linearly with time. And how do we represent a unit ramp signal? For a unit ramp signal, r of t is equal to t for t greater than or equal to 0, and it's 0 otherwise. So when t equal to 1, r of t will be 1. When t equal to 2, r of t will be 2. When t equal to 3, r of t will be 3 likewise. Then we have the parabolic signal, and it's represented by r of t, which is equal to a t square by 2. That is for time t greater than or equal to 0 and r of t equal to 0 otherwise. So this is how we represent the parabolic signal. Like for t equal to 1, r of t is 1 by 2a or 0.5a. So when t equal to 2, you just need to substitute the value of t over here in this equation, a t square by 2. So when t equal to 2, we will get r of t equal to 2a, and for t equal to 3, r of t equal to 4.5a. Unit parabolic means r of t equal to t square by 2. And we have the impulse signal del of t. So its impulse signal is actually considered to be a signal of very large amplitude or very large magnitude, but for a very short duration of time. Right. So del of t is normally represented as infinity in amplitude for t equal to 0, and it's 0 otherwise. Okay. So unit impulse means this del of t will be equal to 1 for t equal to 0, and del of t equal to 0 otherwise. And finally we have the sinusoidal signal. So r of t equal to a simple sine wave with a magnitude a sine omega t. So we can represent the sine wave like this, with the positive peak at a and negative peak at minus a. Okay. So these are the basic test signals. So we have the step signal or unit step, we have a ramp or unit ramp, we have parabolic signal or unit parabolic signal, we have impulse signal or unit impulse signal, and finally we have the sinusoidal signals. Okay, thank you.